As it was just said, I'm going to be talking today about the textural and geochemical diversity of the lunar meteorite Touat 005. Apologies. Touat 005 was found in 2020 in Algeria. It was classified as a fragmental breccia comprised of white plagioclase megacrysts and lithic clasts set in a dark shocked matrix. These megacrysts earning it the name the stained glass lunar. However, a sample of Touat 005 obtained by the University of Western Ontario in 2023 appears very different. The sample is a clast-rich melt rock, aka an impact melt breccia, and it seems to lack the distinct plagioclase megacrysts found in type specimens of this sample, and it displays greater homogeneity, at least in hand specimen visually, than the type specimens of this sample. And so we wanted to investigate why it looked so different. So we used optical microscopy to investigate the textures present in the sample and also the class diversity and various shock features that may be present in this breccia. We used X-ray fluorescence first on the actual hand specimen itself, the full meteorite, before we cut it. This technique allowed us to analyze geochemistry with minimal sample preparation and also without a carbon coat. To evaluate how accurate this data was and the resolution of this data, we also collected X-ray fluorescence maps of the thin sections which were subsequently cut from this sample, and wave dispersive and energy dispersive maps of the geochemistry of these thin sections were also acquired using electron probe microanalysis. Quantitative mineral chemistry was also collected to investigate the various lithic material that was present in this meteorite. And also backscatter electron imagery was used to investigate textures and also further investigate class diversity in the sample as well. So I'd first like to talk in depth about the XRF analysis. So the sample optically in hand specimen looks fairly homogeneous in comparison to the type specimens. However, in XRF, it's revealed to actually be much more complex. And XRF maps of this sample, as shown on the figure to the right here, which is a RGB map of calcium, iron, and magnesium in the sample, there is two distinct fractions that are present, a clastic fraction and a melt fraction that are not visible in optically looking at this sample. And so there's greater heterogeneity revealed when we look at this sample using XRF. I do apologize. The clastic fraction displays major element variability and a much more coarse-grained nature than the melt fraction, which is much more homogeneous in its major elements and is much finer-grained. This analysis allowed us to locate where we wanted to cut thin sections from this meteorite to actually sample this boundary. And 3 thin sections were cut, 2 of which sample the boundary directly. You can see TLB and TLC sample this boundary of both melt and clastic fractions. And another sample was also, thin section was created, which sampled the clastic diversity in this material. And to the XRF and also later EDS maps of these thin sections reveal that the geochemistry of the hand specimen rings true when looking at this sample a lot closer. This boundary is distinct in the geochemistry of the sample, the clastic fraction revealing much more complexity and a much coarser-grained nature than the melt fraction of this material. And there is quite a lot of similarity between the EDS maps and the XRF maps of these thin sections, showing that the XRF actually is fairly accurate and has quite good resolution. And the lack of a carbon coat required to collect these XRF maps shows how useful this tool actually will be to analyze meteorites preliminarily as soon as we get them out of the field and even before we make thin sections from them. So this sample already looks quite diverse and quite complex. I wanted to fully investigate how complex this sample was. So I looked at the class diversity that was present in these 3 thin sections and found that the sample that we have here at Western is much more diverse in the class that are present than type specimens with felsites, quartz monzodiorite present, and various melt rock class with variable textures, as well as anorthosites. Type specimens have only been noted to contain anorthosite megacrysts and plagioclase mineral fragments, which have geochemical similarity to the ferroanorthosite suite. So we are seeing quite a significant increase in diversity in this sample. So does this mean that we are actually looking at the same sample entirely, or are we looking at another meteorite? To investigate this, we compared the mineral chemistry of the thin sections to type specimen geochemistry reported in the classification, found that there is similar calcium content in plagioclase, most notably in ferronanorthosite type clast in 2at005 from Western. There is similar magnesium content in olivine, and there is also similar magnesium and iron content in pyroxene. However, all three of these graphs show that there is much more diversity in the geochemistry and mineral chemistry of this rock. So it is possible that we are sampling quite a variety of material. And to fully investigate this, I compared the mineral chemistry of these clasts in the sample to various lunar rock types that have been studied previously, and found that it is possible that there is not only ferronanorthosite sweet material, there is also magnesian sweet material, possibly alkali sweet material, and perhaps magnesian anorthosites and gabronorites, though further investigation is required to fully confirm this. So this sample is a lot more complex. However, the similarity in the geochemistry at two type specimens means that I do believe that the sample is still 2at005 and reflects the same meteorite rather than another meteorite entirely. However, this brings up an interesting question of pairing relationships of this sample, as it's much more complex in its textural features than the type specimens indicate. And so I wanted to compare two other meteorites that were found in the region of Algeria that this meteorite was picked up in. 2at004 is a feldspathic breccia also found in Algeria, and 2at008 is a troxylating melt breccia, which is found close to 2at005's found location as well. No images exist that I could find of 2at004. However, 2at008 seems to be quite similar in areas in its textures to our sample of 2at005. So there's a possibility that this troxylating melt breccia is actually similar to our sample. And so to further investigate that whether this rings true and these may be paired, I compared the mineral chemistry of these the type specimens of these two meteorites to our sample, found that there is significant overlap in the geochemistry of olivine, of plagioclase, and also of pyroxene. Most notably in magnesian sweet type clast in our sample of 2at005. And this rings true across both the clastic and melt fraction of 2at005, indicating that both of these are derived from the same material. And so it is very possible that these three meteorites are actually paired, and this had not been noted previously. So the heterogeneity that's being shown in the geochemistry, in the clasts that are present, indicate this sample is much more complex than type specimens would indicate. There is more than one rock type that is present in this sample. However, the similarity in the mineral chemistry to type specimens indicates this represents sample heterogeneity rather than an entirely different sample. The variety of material that is present perhaps reflects the variability of material available in the source region of this meteorite. It's possible that this meteorite is sourced from a large impact crater that samples a great variability in geology, or it reflects ejecta input from other craters into the source region of this meteorite. Further analysis and further investigations will be required to further confirm this. So in summary, a sample of 2at005 was acquired by University of Western Ontario, which is texturally different to other hand specimens and shows more heterogeneity in its geochemistry observed by X-ray fluorescence than type specimens, allowing thin sections to be cut to target interesting sites within the sample, this boundary between a clastic and melt fraction, which are not observed optically, which highlights the importance of using XRF to do preliminary analysis of meteorite samples, which is non-destructive and requires very little sample preparation. An increased class diversity present in the sample at University of Western Ontario compared to type specimens may reflect source region heterogeneity, perhaps being sourced from a large crater or sampling ejected from other craters. And I welcome any questions.